All right. So in the last lecture, we talked about Mclaren and Taylor polynomials. In this lecture, we're going to talk about Mclaren and Taylor series, which are special kinds of power series. And it's really not a huge leap from what we did in the previous section. In fact, you'll see that it's really the same thing, with one small minor detail. Okay, so here's how it works. The Taylor series for f about x equals x naught is given by this series, the sum from k equals 0 to infinity of the kth derivative evaluated at x naught divided by k factorial times x minus x naught to the k. Of course, this only works if f is infinitely differentiable. So if you can differentiate it infinitely many times, right? Otherwise, this definition doesn't make any sense, right? So this is the Taylor series. And you'll notice that it's only different from the Taylor polynomial in that our upper limit of summation is infinity instead of n, right? So a Taylor polynomial would end at some finite value n, whereas a Taylor series goes on and on and on forever, okay? So this is the Taylor series. The Mclaren series is similar. It's just that instead of x equals x naught, it's x naught equals 0. So you would just have a 0 here, and this would just be x to the k because x naught would be 0, right? And then you get the Mclaren series. So a Taylor polynomial is just the nth partial sum of a Taylor series, okay? So they're really pretty similar notions. And in fact, in this first example, there's not going to be hardly any work to do because we've already done the work here. So it says, use your work from the previous section to write the Mclaren series for each of the following functions. And we've got e to the x, sine x, cosine x, and 1 over 1 minus x, all functions that we looked at in the previous section. And we came up with Taylor or Mclaren polynomials for each of those, right? So, so let's write down the Mclaren series for them. So for part A, we want the Mclaren series for e to the x. Well, in yesterday's work, we found out that e to the x, the Mclaren polynomial, was 1 plus x squared over 2 factorial, and so forth. Right, so this was the Mclaren polynomial. The summation notation for this would be the sum from k equals 0 to n of, it looks like x to the k over k factorial, right? All right, so this is the Mclaren polynomial. So the Mclaren series would be the sum from k equals 0 to infinity of x to the k over k factorial. And here I'm saying e to the x equals this summation. We're going to talk in detail over the course of the next few sections about what exactly I mean. Like, for what values of x is e to the x equal to this series and stuff, right? But anyway, this holds, at least in some sense, for certain values of x, provided that you have infinitely many terms, right? So it's not just an approximation anymore. It's exactly equal if you can sum up all of the terms of the series, right? So that's kind of a cool thing. Okay. We wanted to do the same thing for part B, was sine x. All right, so in our work yesterday, in the previous section, I should say. So in our work from the previous section, we found this, right, that sine x was approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth. Until we got to -1 to the k times x to the 2k plus 1 over 2k plus 1 factorial. Okay. In summation notation, this would be the sum from k equals 0 to n of negative 1 to the k times x to the 2k plus 1 over 2k plus 1 factorial. So that's the Taylor, or that's the Mclaren polynomial. So the Mclaren series is sine x equals, for certain values of x, sine x equals the sum from k equals 0 to infinity of negative 1 to the k x to the 2k plus 1 over 2k plus 1 factorial. Okay. So I think you get the idea, right? So I'm just going to kind of cut to the chase on the last two. So for cosine x, it would be the sum from k equals 0 to infinity of negative 1 to the k x to the 2k over 2k factorial. And for 1 over 1 minus x, it would be the sum from k equals 0 to infinity of x to the k. So these are some common Taylor or Mclaren series. A Mclaren series is just a special case of a Taylor series, so it's not wrong to call them Taylor series. And so if I slip up, that's, it's excusable. I'm excusing myself. But anyway, yeah, so these are some very common Mclaren series that we'll see, throughout the remainder of the chapter. Okay. This works for Taylor series as well, not just Mclaren series, but Taylor series more generally. So, for example 2, let's use our work from the previous section to write the Taylor series for 1 over x about x equals 1. So we want Taylor series, right? Not the Taylor polynomial, but the Taylor series for 1 over x about x equals 1. So I'm going to have to look this up because I'm drawing a blank. I don't remember off the top of my head what we did in the previous section for this one. Let's see. So for 1 over x about x equals 1. Oh yeah, we did do that. So the Taylor polynomial that we came up with. So for 1 over x about x equals 1, we came up with the sum from k equals 0 to n of negative 1 to the k times x minus 1 to the k. So that's what we came up with in the previous section for the Taylor polynomial for this thing. So the so the Taylor series for this thing. So the series is going to be the sum from k equals 0 to infinity of negative 1 to the k times x minus 1 to the k. Okay, so there's that one, right? So pretty straightforward, right? Taylor series are the same things as just Taylor polynomials, except that you allow the upper limit of summation to go to infinity instead of stopping at a finite value n. Of course, that's not all we're going to talk about in this section, though, right? So because this yields an interesting question just about these kinds of series in general, these kinds of power series. Like I said, Taylor and Mclaren series are special kinds of power series. A power series more generally is just any series of the form c sub k times x to the k, where the ck's are constants and the x is a variable. And so what's different about power series from the series that we talked about in sections 9.3 to 9.6 is the presence of a variable, right? So the series we looked at in 9.3 to 9.6 were just series of real numbers, okay? But now we've got a variable thrown into the mix. And so when you replace that variable with a real number, the resulting series may converge or diverge. And so it yields an interesting question, like for what values of x does this power series converge or diverge? And of course, that's going to depend on what the power series looks like, right? But it turns out that we can solve for x. We can solve for the values of x for which this kind of power series will converge or diverge. So the set of x values for which a power series converges is called its convergence set. And theorem 9.8.2 describes the convergence set for a power series in x. Okay, so it turns out, and we're not going to prove this theorem, but it turns out that exactly one of the following is true for any power series in x. Right? So for any power series in x, exactly one of the following is true. The series converges only for x equals 0. And by the way, all power series in x converge for at least x equals 0. Right? Why? Well, because this is what the power series looks like. If you plug in 0 for x, you're just going to get the sum of 0 added to itself infinitely many times, right? It's just going to be 0 plus 0 plus 0 plus 0. Of course that converges, right? It converges to 0. So this thing is always going to converge for at least x equals 0, right? So so the series converges only for x equals 0. That's one possibility. Another possibility is that the series converges absolutely for all real values of x, right? So no matter what you plug in for x, the series will converge, right? So that's another possibility. And then the third possibility is that the series converges absolutely on a certain interval, okay, from negative r to r. This interval is, of course, centered at 0, okay? But the series converges absolutely on some interval centered at 0. We call r the radius of convergence. We'll talk about that in a second, okay? But it converges on negative r to r for some real number r, and then it diverges outside of that interval. So if x is less than r or if x is greater than r, it diverges, okay? This still yields a question, you know, like, well, what happens right at negative r and right at positive r? We know if x is greater than negative r but less than positive r, it's going to converge. We know that it's going to diverge if it's less than negative r or greater than positive r. But what happens when x equals negative r or when x equals positive r? Well, there it may converge absolutely, or it may converge conditionally, or it may diverge, right, at those two locations. And that just depends on the series. Okay. So broadly speaking, we can think of the convergence set as an interval in all three cases, right? We can think of this as an interval with a radius of 0, okay? We can think of this as an interval with a radius of infinity, and we can think of this as an interval of radius r, okay? So since the convergence set is always an interval, we call it the interval of convergence, and we call r the radius of convergence. And again, r could be 0, infinity, or some positive real number, any real number. Okay? So with that in mind, let's find the interval of convergence and the radius of convergence for the following 4 series. This might take a while, but I think this is a really great set of 4 examples. And I'm not patting myself on the back because I stole them straight from the book, of course. but they're really good examples, okay? Because they're going to illustrate each of the cases really well. So this is example 3. We want to find the interval and radius of convergence for each of the series. So we're going to start with sum from k equals 0 to infinity of x to the k. Now, the way that we do this is we're going to apply the ratio test. actually we're gonna apply the ratio test for absolute convergence, right, as your book calls it. And this will help us to find the radius of convergence. So to do that, right, we take the limit as k approaches infinity of a sub k plus 1 divided by a sub k, right? And actually we're going to be doing the absolute values of these things. So in this case, that's going to be absolute value of x to the k plus 1 divided by absolute value of x okay. So that equals absolute value of x times absolute value of x to the k divided by absolute value of x to the k. Oh, I need my limits, right? I need to rewrite the limit symbol each time. Okay, but those cancel. So this is just limit as k approaches infinity of absolute value of x. Okay, so limit as k approaches infinity of absolute value of x just equals x, right? It just equals, well, it equals absolute value of x. And so when we apply this test, what we need is for, in order for this thing to converge, we need this thing to be less than 1, right? So this series converges absolutely if absolute value of x is less than 1. By the way, that's the same thing as saying that x is between -1 and +1, right? But there's our interval, right? So it converges absolutely from -1 to +1. It's going to diverge if x is less than -1 or if x is greater than +1. And what happens at -1 and at +1 themselves, right? What happens at those values? So we still need to figure that out, right? So it's going to converge absolutely on -1 to +1, but we don't know what happens at x equals -1 and at x equals +1. So let's look at what happens there. At x equals -1, what series do we get? Well, if we plug in -1 for x, we get the sum from k equals 0 to infinity of -1 to the k, which diverges, right? This is just the sum 1 minus 1 plus 1 minus 1 plus 1 minus 1 1 and so forth. And we've proven that this thing diverges. We proved this way back in like 9.3 or something. So it diverges. Okay, at x equals +1, we get the sum from k equals 0 to infinity of 1 to the k, which is just going to be 1 plus 1 plus 1 plus 1 plus 1. Okay, that also diverges. They kind of diverge for different reasons, right? This one diverges because the sequence of partial sums alternates between 0 and 1. Okay, so it doesn't approach any value. This one diverges because the sequence of partial sums goes off to infinity, right? So that one diverges. But in any case, they both diverge. So now we've answered the question completely, right? We know that this series is going to converge. So therefore, the series from k equals 0 to infinity of x to the k converges on negative 1 to 1 and diverges elsewhere. Anyway, so there's our interval of convergence, right? So our interval of convergence negative 1 to 1. The radius of convergence would be r equals 1, right? Because this interval is centered at 0, and so clearly from the center of the interval to the end of the interval is 1 unit in length. So there's the radius of convergence there. Okay, let's do another one. By the way, so this was a case 3, right? This was a case 3. Or a case C, I guess I called it, right? So because the series was converges absolutely on an interval, okay, and then diverges elsewhere. It didn't converge for all real values, and it didn't converge only for 0, right? Well, let's look at another example. So let's do sum from k equals 0 to infinity of x to the k over k factorial. Okay, so again, to find the interval and radius of convergence, we're going to apply the ratio test, right? The ratio test for absolute convergence. Okay, so we're going to take limit as k approaches infinity of a sub k plus 1, absolute value of a sub k plus 1 divided by absolute value of a sub k. That's going to be limit as k approaches infinity of x to the k plus 1 over k plus 1 factorial times k factorial over x to the k. Oh, with absolute values everywhere, of course, right? Absolute value of this thing times absolute value of that thing. Okay, that's going to be limit as k approaches infinity of x to the k times x over k plus 1 times k factorial. You can, okay, so absolute values. While we're talking about this, maybe we should just say, right, like this thing is positive, this thing's positive, so the product is going to be positive. If you take absolute value of everything individually, everything's still going to be positive, right? So like I can just throw absolute values around all this stuff kind of like individually, and it doesn't change it doesn't change any it doesn't change the outcome, right? Anyway, so that's helpful because it'll allow me to cancel stuff easily, right? That cancels that, that cancels that. So this is equal to limit as k approaches infinity of absolute value of x over absolute value of k plus 1. Everything else got canceled. Now x is always some fixed number. It's unknown. Okay, it's unknown, but it's fixed. So maybe it's a really big number, like 3,000 trillion or something, right? Like maybe it's some huge number, but it doesn't matter. It's fixed. So as k gets really large, and the numerator is fixed, the denominator is going to get bigger and bigger and bigger and bigger. So the number is going to get smaller and smaller and smaller. This thing's going to go to 0, right? So this limit is 0. If you don't like that argument, you could say, well, look, I'm taking the limit as k goes to infinity. X doesn't rely on k at all, so I can take x out of the limit, right? I can call it absolute value of x times limit as k goes to infinity of 1 over absolute value of k plus 1. And by the way, I can drop the absolute values at this point because k is a positive number if it's going to positive infinity, right? So, but anyway, that's going to go to 0, right? That's going to go to 0. So this is going to be absolute value of x times 0, which is just 0. Okay. That's interesting, right? Because what that tells us is that regardless of what we plug in for x in our power series here, regardless of what we plug in for x, the ratio test is always going to end in 0, which, by the way, is less than 1. So this limit is less than 1 for all real numbers x. That means that it converges for all real numbers x, right? So this is less than 1, right? So we can say since limit as k approaches infinity of ak plus 1 over ak is less than 1 for all x, the series converges for all real numbers x. So the interval of convergence so the interval of convergence is negative infinity to positive infinity, and the radius of convergence is positive infinity, right? So r equals positive infinity, we'll say. All right, so there's the interval and radius of convergence. Interval and radius of convergence for this series. Okay, so all reals. Now, by the way, it's not because you got 0. It's because this limit was less than 1. So if we had ended up with something like 9/10, then the same thing would be true, right? That, this thing would be less than 0 for all reals x. Now contrast that with what we got up here, right? When we took the limit here, we didn't get a finite, or we didn't get a number, we got absolute value of x, right? And so this thing will converge only if the absolute value of x is less than 1, right? And diverge if it's greater than 1. All right, so let's look at a couple more. Okay, so let's do this for the sum from k equals 0 to infinity of k factorial times x to the k. So again, we're going to apply the ratio test for absolute convergence. So we'll look at limit as k approaches infinity of a sub k plus absolute value of ak plus 1 over ak. Right, that's limit as k approaches infinity of k plus 1 factorial x to the k plus 1 over k factorial x to the k. Everything in absolute values, right? Boom, 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 and boom. I guess, these k plus 1 factorials, if k is going to infinity, this is a positive number, this is a positive number. The only thing we don't know about is these x's, because x could be positive or negative. So, we still have to have absolute values there. But, okay, so this is going to be limit as k goes to infinity. K plus 1 factorial is, as usual, right? K plus 1 times k factorial times absolute value of x to the k times absolute value of x over k factorial times absolute value of x to the k. So those are going to be gone. Those are going to be gone. We're going to get, it looks like, everything canceled except, okay, so it's going to be limit as k goes to infinity of k plus 1 times the absolute value of x. And again, if you like, you can pull out the absolute value of x, since it doesn't rely on k. Okay, that's going to be some fixed number times infinity, which is just positive infinity, regardless of what x is, right? this part's going to go to infinity. So x times this thing is going to go to infinity. Doesn't matter because x is a fixed value. So that's an issue, right? That's an issue because that means that it doesn't matter what we plug in for x. We're always going to get infinity when we apply the ratio test. Now, there is one caveat here, because notice that in order to apply the ratio test, we had to divide by x to the k. Well, if x is 0, then this expression is meaningless, right? So I should have said for x not equal to 0, right, this stuff holds. So this is always greater than 1, obviously, for any x. For any x not equal to 0, I should say, right? Now, if x equals 0, then this is just going to be 0 plus 0 plus 0 is going to converge, right? It's going to converge to 0. So this is one of those case A types of situations, right? Where the series converges only for x equals 0. It's going to diverge everywhere else. Because no matter what else you plug in for x, when you apply the ratio test, you're going to get positive infinity. And again, just like in the previous case, it's not that we got positive infinity that tells us this. It's that this limit is always bigger than 1. So even if we had gotten like 14 or something, or like the square root of 7, right, as our limit, because that number is always bigger than 1 for any x, we can conclude that this thing is going to diverge unless x is 0. Right? So this series diverges for all x not equal to 0. Okay, so the interval of convergence, well, there isn't really an interval of convergence. I'm not sure what your book will say. Maybe it'll say something like none. Really, the convergence set, is just the set made up of the single element 0, right? But you wouldn't put parentheses or brackets around that. This doesn't mean anything. Well, it does. It means a lot of things, but it doesn't mean what you think. And neither does this, right? So you put brackets around it, right? The radius of convergence. R equals 0 in this case, right? So there's your convergence set, and there's your radius of convergence. Okay, so it only converges for 0. This is a really boring series, actually, because it diverges everywhere else. Okay, so what have we seen so far? So part C was an example of the first type of outcome. Part B was an example of the second kind of outcome. And part A was an example of the first kind of outcome. Let's do one more. So this one's kind of a wild card. We don't know what we're going to get. Okay, let's do sum from k equals 0 to infinity of -1 to the k, x to the k, over 3 to the k times k plus 1. Okay. So same deal here, right? We're going to apply ratio test for absolute convergence. Take the limit as k goes to infinity of absolute value of ak plus 1 divided by absolute value of k. When we take the absolute values, the -1 to the k thing just disappears, but I still need absolute values around the x because x could be a negative number, right? So so this thing disappears. This thing I'm going to put absolute values around. I'm not going to worry about absolute values anywhere else, but this is going to be absolute value of absolute value of x to the k plus 1. I was about to add 1 on the wrong place, right? Over 3 to the k plus 1 times k plus 2 times 3 to the k times k plus 1 over absolute value of x to the k. All right. So I'm going to have absolute value of x to the k times absolute value of x over 3 times 3 to the k times k plus 2 times 3 to the k times k plus 1 over absolute value of x to the k. So that will cancel that. That will cancel that. And I think that's all I get. That's all right, though. So this is going to be limit as k approaches infinity of absolute value of x times k plus 1 over 3 times k plus 2. So again, I'm going to pull out the stuff that isn't dependent on k. I guess I don't need the parentheses anymore. But anyway, as k goes to infinity, this thing goes to 1, right? So we just get absolute value of x over 3. Okay. So this is a type 3 situation, right? Because this thing is going to converge so long as this is less than 1. Okay? So, and it's going to actually, it converges absolutely if this thing is less than 1. So we'll say x to the k over 3 to the k times k plus 1 converges absolutely if absolute value of x over 3 is less than 1, which implies absolute value of x is less than 3. Right? So our interval of convergence would be -3 to +3, and our radius of convergence would be 3. All right. The only thing we need to figure out, though, is what happens when x equals -3 and when x equals +3, right? So in other words, this is our interval. X is between -3 and +3. What happens at -3? We know that if x is less than -3, it diverges, and if x is greater than -3, it converges, but what happens when x equals -3? So let's figure that out. So if I plug in -3 for x, then the series I get is the sum from k equals 0 to infinity of -1 to the k times -3 to the k, right? I'm plugging in -3 there, over 3 to the k times k plus 1. That's sum from k equals 0 to infinity of -1 to the k. -3 to the k is -1 times 3 to the k, and I can distribute that exponent to the -1, so I get another -1 to the k. And that's nice because that cancels that. These things will cancel, right? Because if k is an even number, then they're both positive anyway, so they don't do anything. If k is an odd number, then they're both negative, and a negative times a negative is a positive, so those things cancel each other out. So this is the sum from k equals 0 to infinity of 1 over k plus 1. And then if you imagine plugging in values for k, like if you plug in 0, you get 1 over 1, which is 1. If you plug in 1 for k, you get 1/2. If you plug in 2 for k, you get 1/3. So you get the series 1 plus 1/2 plus 1/3 plus 1/4. That's the harmonic series, right? And we've proven that the harmonic series diverges. Okay. Okay, so when you plug in -3 to this thing here, you just get the harmonic series, which is divergent, right? What about when x equals positive 3? What happens there? We get negative 1 to the k times positive 3 to the k over positive 3 to the k times k plus 1. Those things will cancel. You get negative 1 to the k over k plus 1. This is the alternating harmonic series, right? Right? So this is the series 1 minus 1/2 plus 1/3 minus 1/4. And we've proven that the alternating harmonic series converges. We proved that in, what section is this? This is 9.8, so we proved that in 9.6 when we talked about alternating series, right? Which converges. So right, it's the alternating. It's the alternating harmonic series. So it converges. Okay, so that's interesting. So on the left endpoint, negative 3, it diverges. But on the right endpoint, positive 3, it converges. What did I say? It diverges here, but converges there. Okay, so the interval of convergence is going to be negative 3 to positive 3, but we put a bracket on the positive 3 because it converges at x equals positive 3, right? It diverges at negative 3, but converges there, and then it converges everywhere in between, right? So there's the interval of convergence on that one, right? So that gives you another kind of case 3 scenario, but it just goes to show you that on the endpoints, you don't know what's going to happen. You have to check. You have to check you have to check to see what happens on these endpoints. Okay, the radius of convergence is still 3 here, right? Okay. So so far, we've been looking at these power series that are centered at 0. You could have power series centered at some place other than 0. You could have a power series centered at x naught, right? So for a power series in x minus x naught, right, this is a power series in x minus x naught, exactly one of the following is true. And then you have the same cases as you did for power series centered at 0, okay? Either the series converges only for x equals x naught, right? Or the series converges for all reals, or the series converges on some interval x naught minus r, x naught plus r, right? Where r is your radius of convergence. You don't know what happens at the endpoints, so you have to actually test those, okay? So let's do an example of that, and then we'll call it good for this section. So let's find the interval and radius of convergence of this guy, x minus 5 to the k over k squared. Oh, we're starting at 1. I don't know why we're starting at 1 instead of 0, but let's do it. So we've got sum from k equals 1 to infinity. My sigmas are getting worse and worse. Of x minus 5 to the k over k squared. Okay. We do this the same way, right? We do this the same way. We're going to apply the alternating series, the ratio test for absolute convergence. So we're going to look at limit as k goes to infinity of x minus 5 to the k plus 1 over k plus 1 squared times k squared over x minus 5. And really I should have absolute values here. Absolute value of x minus 5. Okay. we've got absolute value of x minus 5 times absolute value of x minus 5 to the k over k plus 1 squared. I'm not going to bother expanding that because it's not going to cancel with this thing, unfortunately. I love it when things cancel. Okay, but those will, anyway. Oh, no, this should be to the k, right? So actually, this cancels that and leaves that, which is better, right? Which is better. So my apologies. These things are gone. This thing remains. Okay, so we've got limit as k approaches infinity of absolute value of x minus 5 times k squared over k plus 1 squared. I can take out the absolute value of x minus 5. K squared over k plus 1 squared. Well, you know, you've got a polynomial over a polynomial. The limit as k goes to infinity is going to be the ratio of the leading coefficients, which is going to be 1 over 1. So this thing goes to 1. 1 times absolute value of x minus 5. Right? So you get absolute value of x minus 5. So this thing is going to converge as long as this thing is less than 1. Right? It's going to converge absolutely. Okay, now what does that mean? That means that x minus 5 is between negative 1 and positive 1. So if you add 5, x has to be between 4 and 6 in order to converge. Right? So x has to be between 4 and 6. So there's our interval of convergence. Now the only question is what happens at 4 and what happens right at 6. Okay? Because certainly if x is less than 4, it diverges. If x is greater than 6, it diverges. If x is between 4 and 6, it converges. But what happens when x equals 4? What happens when x equals 6? So let's see. So at x equals 4, I'm going to plug in 4 for x here. I get the sum from k equals 1 to infinity of 4 minus 5 to the k over k squared. So that's the sum from k equals 1 to infinity of negative 1 to the k over k squared. Well, remember that if the absolute value of the series converges, right, then the series converges. The absolute value of this thing is just 1 over k squared, which is a p series, right, with p equals 2. It converges, right? So this thing converges, right? Which converges. Right? It's a p series. P series with p equals 2, which is greater than 1. Okay. When x equals 6, what happens? We get sum from k equals 1 to infinity of 6 minus 5 to the k over k squared. That's the sum from k equals 1 to infinity of 1 to the k over k squared, which is, of course, just 1 over k squared. And again, that converges. You know, p series again, with p equal to 2, which is greater than 1. So it converges at both. This one converges at both endpoints. Okay, very interesting. So the interval of convergence is 4 to 6, this time including both endpoints, right? Because it converges at both endpoints. Radius of convergence r equals 1. Okay, r equals 1. You can see that here, right? This is the radius of convergence, but you can also see it just because, you know, the length of this interval is 2. So from the center of the interval to the end point of the interval is going to be length 1, right? So the radius of convergence is 1. Okay, so that concludes it for the examples. But what I want to point out to you is that we've seen all of the possible cases. So this was a beautiful set of examples, really. So so we saw an example of a series converging only for x equals 0. That was example. That was example 3. That was example 3c. Okay. We saw an example of a series that converges for all real values of x. That was example 3. That was example 3b. 3b. Okay. And then we saw 3 examples of the third case, where the series converges on some interval, but then you have to check what happens on the endpoints. And one of the examples that we saw was example 3a, where it converged on the interval but diverged at both endpoints. Okay, diverged at both endpoints. We saw an example where it converged on an interval but diverged on one of the endpoints and converged on the other one. That was example 3d. And then the example that we just worked out, right? So example 4 was one where it converges on an interval and converges at both endpoints, right? So anything could happen at the endpoints is the moral of that story. But I think we've seen a good set of examples here. Sorry if I'm making you dizzy by switching pages so much, but I just wanted to point out that you know, that was a really good set of examples that your book came up with. They must have been smart guys who wrote your book. But anyway, that's that.